All right, so motion, circular motion, we're going to be talking about in chapter 6, basically in chapter 7 too, but this is the idea. If you're driving a car around the corner, okay, you got a ball on a string zinging around. If you are a planet and there's another planet out here orbiting you, okay, there's always something pulling you in. And that force is acting to pull you in to the corner so you don't slide off. You with me? And so sometimes it's because of the tension in the string, sometimes it's because of friction, sometimes it's because of gravity. That force always pulls you towards the center. That's why you go around the corner. This is a center seeking, as we say, force. And it's by definition called centripetal force. Clearly, the force you experience is going to be harder the smaller the radius. And as radius gets smaller and velocity goes up, then as those two things happen, this goes up and the radius gets smaller. What ends up happening is you get a bigger force. Okay, so it turns out that force, of course, is always ma. Obviously, that's what our boy Newton would say. But specifically, centripetal force is m times v squared over r, where v squared over r is equal to your centripetal acceleration, a sub c. Okay, now where does it point? That force always points towards the center of the circle. That's the direction it goes, because as you know, force is a vector. So is acceleration, so is velocity. They're all vectors. Okay, so I'm telling you, I'm going down the road like so. Going into this corner doing 90 meters per second, and the radius of this curve is 10 meters. What kind of acceleration are we going to have here? By the way, does it matter what the mass of the thing is in terms of total amount of force? Yes, but in terms of acceleration, no, it doesn't at all. Meaning that a light car and a heavy car going on this corner on the same tires, everything else being equal, will behave exactly the same way. And why is that? Well, because it's all about the acceleration, okay, and the radius of the corner. Okay, and well, then of course their friction was holding them on. It has to do with the tires and the road surface, but that's all the same. There won't be any difference in terms of mass. So 810 meters per second squared. Wait a minute. That is 810 divided by 9.8. That's roughly 83 Gs. Groom, that's ridiculous. Sure is. Well, that's crazy. I mean, like 3 or 4 Gs would be a lot. Correct. Well, how would they make this happen? Well, if you're racing a NASCAR, first of all, we wouldn't be going on a 10-meter radius curve. We'd be going on a 100-meter radius curve. How would that change things? Well, that would make this 81. 81 divided by 9.8 is 8-ish. So about 8 Gs. Like, that's still too much. True. But remember, on a race course, they always bank the corners like so. Why? Well, partly because as you go in the corner, there's a parallel force that's trying to push you where? Down the hill, right? There's friction that's working against you sliding off, so friction is also trying to hold us on the hill. And centripetal force is also holding us on the hill. And so we can take a lot more going around a corner when it's banked. We'll talk more about that later on. Okay? Okay. You're on the freeway. Whoa. The radius of this curve is like 300 meters. Yeah, probably. Maybe 400. Let's do 400 meters. Quarter mile. Whoa, it's way over there. Yeah, how fast are you going? I don't know. 30 meters a second. Okay. Well, 30 squared divided by 400 is, well, roughly 2.25 meters per second. squared, which is, dang it, 2.25 meters per second squared, which is less than it's about a quarter of a G. Which is why when you drive down the freeway, you see these curves, they're super long corners. They're like basically straight road, right? And maybe it's over there 3 or 4 miles. That's why you can drive around those corners, quote unquote corners on a freeway, doing 90 mile an hour, because it's for all intents and purposes straight. Okay, so that's pretty straightforward kind of thing, pretty easy to do. What if I were to do this in a vertical circle? Now this is where it gets interesting. Okay, if you should do this at home tonight, I will ask you later in this week what you thought about it. But there's the gist of it. When you're running this is a weight here, like a rock or something, there's a string, and you put it in a vertical circle like this. Oh, this is a vertical circle, not a horizontal. Okay. Well, what you'll notice is that if you're not going fast enough, what does it feel like when you come across the top? You can get to when you get to just the right speed, okay, when you're getting to just the right speed, what you find is that gravity and the opposite of the force, the centripetal force, the reaction force, are the same, which means you will feel weightless at the top if you go at a certain speed. We call that the critical velocity, because if you go any slower than that, what happens? Well, you're no longer in orbit, and then you're going to plop in, because the string is just a wet noodle, okay? And it will not hold you there, okay? And so when you do this, you're like, oh, well, what do you got? Well, at the bottom, you've got the mass is mv squared over r plus mg, because if there's nothing else, okay, you've got this force coming downwards at you, yes, and then, which is your mass, mg, right? So you got mg pulling down. And you got the reactionary force, because again, what did Newton say? F equals ma. Yeah, he said that. Inertia, he said that. But he also said equal and opposite reactionary force, right? There's a force in the string pulling you inwards, but the reaction to that is going the other way. And what is it? It's equal and opposite reaction. So the string, if it's going to break, it's going to break at the bottom. Here, this mv squared is pointing off to the side. The mg, of course, always pointing down. Okay? And you can see that going this direction, this is kind of pointed up, mv squared over r. And mg, of course, is always pointing down. What happens when you get to the top? Well, mv squared over r is going that way. Gravity is going this way. Oh no, because it's always going that way. And the idea is, if you're going the right speed, what happens to the string? The string becomes flaccid because there's nothing to hold it apart. And so when you do this, you get mv squared over r is equal to mg. Of course, the masses cancel out, which gives you the thought that what? It doesn't matter how heavy the thing is, because, well, it doesn't. And so, as you can see, the critical velocity is simply the radius times gravity. So if you had a radius of a 3-meter string, how fast would you have to spin it? Well, it'd be the square root of and you get 5.4 meters per second was what you'd have to spin it at in order to keep this thing from going limp at the top. If you went 5.4 meters a second at the top, you would feel weightless. You would literally, if you were on that ball, you would actually feel weightless at that point. And it's kind of cool because when you start thinking about it, you're like, oh, interesting. I wonder if that's why in outer space we do things like, for instance, they used to do what's called artificial gravity in a lot of our space stuff back in the day. Well, they would spin things and you'd actually create an artificial gravity, because if you're on a deal like this and it was spinning, and everything would be forced towards the outside, and you would be standing on this outside, and you, whichever direction you'd be going. But the idea is that you would feel like you had some weight, because centripetal force is pushing you against the sidewall's pushing back at you, and then you didn't feel weightless anymore because there was some pushback against you. When you feel weightless, it's because there's no pushback on you at all. Okay, right. Excuse me. There is this Excuse me. Think about this. If you're on a banked hillside like so, and you're here like so on your car, let's say going around this hillside, you are going around the track, coming towards us out of the page. Okay, there's obviously some parallel force that wants to pull you in. Okay, there's some force parallel. What do we know about that? That force parallel is equal to mg sine theta. Okay, and that's cool because that's actually equal to, that's actually going to be equal to and so that's the force parallel. And then of course your force normal, which we use for friction, is what? Mg cosine theta. Okay, and listen, if you have no friction at all, if there is no friction at all, none, then all you would have to do is this. You'd have that, oh, I'm going to die. This here is your force, centripetal force too, because centripetal force always pulls in the direction of the circle. Well, the direction of the circle is down this direction, yes? So then you would say that mg sine theta is equal to mg cosine theta if we're not coming off the track, yes? Okay? And so if you do this, this is in the absence of any friction at all. Okay? And then when you divide this out, what you end up with is you end up with sine over cosine, okay, is equal to what? So you're like, oh, well, I gotta be careful for a minute here. So if this is true, back to train up here. So this is equal to mv squared over r. And so if that's equal to the force normal at that point, which is mg cosine theta, what you end up with is, when you do the math, you end up with this thing right here. You end up with the tangent of theta is equal to v squared over gr. And again, that's because right. Hold that thought. Okay, we just divided. What we end up doing is you just end up dividing both sides by, so if you have f sine theta, or that is mg sine theta, which is mg sine theta, but it's also equal to mv squared over r. If you divide that guy, ouch, my nose, got me bananas. If you divide that guy by f cosine theta, and you divide this by cosine theta over here, okay, right. Oh, well, I'm sorry. And if this side is just mg, that's how your book writes it. It's just mg. The cosine theta is, we worried about on the other side. So if you do that, then you end up with, as I said, the tangent of theta is equal to mv squared over rg. Or no, it's v squared over rg. V squared over rg. There you go. Yay, because the m's cancel out. There you go. Right. That's it. Perfect. So then what does that mean? That means that if you wanted to go out and go around a corner, at any corner, how fast could, or what would you have to bank this corner out to have no friction and still stay on the hill? This is in the case of no friction. Then, of course, what would happen if you added friction to this mass? Well, if you added friction, then if there's friction, then you can make it a bigger angle. Yes, we'll talk a little bit more about that in the coming days. This has to do with, yes, going around a corner like this. It also has to do with banking your airplane around a corner as well, right? It has to do with that as well. We'll talk a little bit more about the applications of this. This is how fast you need to be going to go around that corner. Okay, so if the radius of the curvature was, I don't know, 10 meters, and you were going, and this angle was 30 degrees, okay, and the velocity was 30. Well, let's just say, what is the max velocity? Okay, what would the maximum velocity be? Well, I need to take the tangent of 30. Make sure you're in degrees when you play this game. So the tangent of 30 times 9.8 times 10 meters, and then square root that. So about 7.5 meters a second. If you're going about 7.5 meters a second, or a little bit lower, you will stand this hill no problem without the friction. If there's not any friction there and you go faster than that, you're going to come scooting up the hill. Yes, now you're going to spin out, we say. Okay, has to work out that way. So that equation will get tweaked a little bit when we add friction to it. And that's something that we'll look at a little bit later on in this chapter. Not very difficult though. Okay. And the last thing I want to mention briefly today, although we're going to come back to it, is we all know about gravity. Gravity is a pretty cool thing. Obviously, what does it have to do with? You have two bodies, two celestial bodies, mass 1, mass 2. How much force do they exert on each other? Well, they exert the same force, first of all, on each other. Because why? Because the one pulls one way, the other pulls the other way, the opposite, equal and opposite amounts. Okay, so that's clear. But the force of gravity, what does it have to do with? Well, it has to do with the distance between them squared. So as the distance gets twice as big, the force of gravity is a quarter as much as it was before. Okay? And then you're like, well, isn't it something like mass 1 times mass 2? Yes, theoretically this is true. We say this is proportional, but it's not equal. And it's not equal until we multiply through by a constant. And so that constant is what's called the gravitational constant. And it's big G, M1, M2 over R squared. Where big G is, let's see if I can do it by memory, 6.67 times 10 to the minus 23? No, minus 11. Minus 11. Well, that's close. No, it wasn't close at all. All right, there it is. What would that be measured in? This needs to be newtons. Yes? So this is kilograms. This is kilograms. So it's going to be kilograms squared. I need to get rid of kilograms squared. Obviously, I need to get newtons when I'm all done. This is in, so I need to get, this is going to be in meters squared currently. So I'm going to need to multiply by meters squared, I guess. And then times by newtons. So theoretically, newtons, meters squared per kilogram squared is what that's technically in terms of. Okay? Mr. Groom, it feels like gravity is kind of weak. It's totally weak. It is the weakest of all the forces. It's by a darn sight. By a darn sight. Mr. Groom, can we find out how much force the sun expands on the earth? We sure can. The mass of sun is... One moment, please. I have that not memorized, but I remember where it lives. Well, that's not true. Maybe I do. Mass of the sun. Ah, crap. I swear it's here somewhere. Oh, I don't care. I'll giggle it and I'll tell you what it is. Sun, mass. No. Well, piss on it. We'll just look it up. We'll just giggle it, kids. Mass of the sun times 10 to the 30th is what I want to say. I want to say it's 2 times 10 to the 30. Is that right? Hey, how about that? 2 times 10 to the 30. I'm rolling with it. 2 times 10 to the 30 kilograms. Mass of Earth is... Gosh, I can't remember Earth. I should, but I don't remember it. 10 to the 24? I want to say it's 10 to the 24. It is. 6 times 10 to the 24. Good criminy, I'm on fire today, boys and girls. 10 to the 24. And how far are we away? 1 astronomical unit. That's true, but we need to have it in meters. Distance, sun and Earth. Yeah, 150 million kilometers. So 150 million. Now that's in kilometers, ain't meters, so that's meters, yes? So if you're doing the math on this, on top, you're getting a god-awful big number. Divided by, that's 3, 6, 9, 11. So you're dividing by 1.5, e minus 11 on the bottom. So when you, squared, sorry, that's going to be e minus 22. So hold the phone. When you divide by a teeny tiny number, you make your other number even bigger, yes? So the top's going to be 10 to the 54 roughly. I think it's technically 55, whatever. This is 10 to the minus 22. So you add, you minus exponents, 54 minus 22 is, minus a minus 22 is 76. Okay? We're looking at 10 to the 76. And you're like, well, that's a lot. Yeah, but then we're going to multiply by 10 to the minus 11. So it brings it down by quite a bit. So it's a monster number. So G, big M, little m over R squared. So big G is 6.67 e minus 11. 2 times 10 to the 30. Six E24 over 1.5 e minus 11 squared. Get your calculator out. So 6.67 e minus 11 times 2 e30 times 6 e24 divided by 3.55 E6 newtons. 3.55 E66. What did I say? E1 did I say it was? E66 newtons. Oh, right. I said this is about 76. Technically, it's technically it would be about 77. 1077. And then, of course, you multiply that by 10 to the minus 11. And you get 10 to the 66. I said this was approximate. It wasn't 10 to the 76. It was 10 to the 77. Anyway, it's a lot of newtons. But, it's by far the weakest of the natural forces. By far. So I am close. It's way smallest. All right, that gets us started on this chapter. And we'll make another video in the coming days.